All right, we're going to get right to it. We're going to go through some of the example problems in this worksheet, which is on quantitative graphs and their functions. We're going to incorporate some calculus too. So I'm going to do problem number one. I'm going to skip number two, and then we're going to do problems number three and four on there. So problem number one gives us a velocity time graph with some numbers to use here, and it wants us to sketch any of the missing curves. So I know right away that the slope of this velocity time graph is going to give me the acceleration. I can see that that is a negative constant slope, so that's going to tell me that I can plot a negative constant acceleration. And I'm going to try and get the number value from that from the slope here in a second. In terms of the position time graph, I don't know where to start, so I'm just going to start at 0 meters. But I do know because this is 20 meters per second on the y-intercept right here, and the y-intercept is going to give me my initial value for velocity, which is v naught, then I know that's going to be equal to 20. So that's going to appear then as a positive tilt on my position time graph, right? Because a positive velocity of 20 corresponds to a positive tilt initially here. It's going to hit 0, and then it's going to end up slightly negative. And actually, it's going to end up, if we want to be exact, at an ending speed of negative 5 meters. So this is going to create a parabola that is going to reach a vertex and then return just slightly to a negative steepness. So the flat vertex here corresponds to the 0 point there. Okay, so we've sketched our graphs. Now what we'd like to do is we're going to determine numerical values for all of these different quantities. And so the first thing we want to do with any quantitative graph, which is a graph that has numbers, is we're going to look at what's on the y-axis and what's on the x-axis and think what quantities we can get using that variable. So for example, velocity is on the y-axis. So I can get the variables v naught and v, just like I did, 20 and negative 5. My time is going to be 4, so I can get the time. If I then look, instead of the x and y axis, at the slope, I already mentioned that's going to give me the acceleration. So if we look at the rise of a run, it's going to be going down to negative 5 and over 4. So our slope, which is acceleration, should give us negative 25 over 4, which equals negative 6.3. And this is our slope, and that's going to be the acceleration. So that actually gives me my constant acceleration. There's no function for this. It's just simply negative 6.3. And since I know my y-intercept is already 20, I can actually go ahead and write this function. It's going to be negative 6.3, which is the acceleration, times time plus 20. So that's our linear equation in slope-intercept form. We have our slope of 6.3 and our y-intercept of 20. We know that that represents the acceleration when we do slope of a velocity time. And we know that the initial velocity, since velocity is on our y-axis, the y-intercept would be our v naught, our initial velocity. So in going to the xt graph, because I'm using functions here, I can do an integral. Just like if I were to go to this one, I could use a derivative. And if we notice the derivative of this function, if you go ahead and try that, should give you negative 6.3. When we do the integral of this function, we're going to raise this to a square, right? We're going to add a power and then divide by that. So we're going to turn this into t squared and then divide by 2. So that gives us negative 3.15, right? We're going to do the 6.3 divided by 2. So we get our negative 3.15 t squared, and then we have plus 20t. And just like when we were first going from the sketching part, from this velocity time graph to the position time graph, and I was saying, well, we know our initial velocity is 20, so we know this is going to be tilted positively. I didn't know where on this position axis to start. Notice that I just started right here because I didn't know where else to start. Same thing here. So if there were an x naught, I wouldn't have any idea what that is. So we're just going to assume that that's 0. The problem would have to tell us if there was some starting point. There's no way for us to know that just given this velocity time graph or given its velocity time function. So if we assume that this is 0 just because we didn't know any better, so if we don't know any better, we can just make it 0, then my delta x is something I'm going to have to calculate. Now, I have a couple different ways I can do that. I could use this function, right? X is equal to negative 3.15, and then if my time is 4, I can sub that in for time. And that gives me 29.6 meters. Or I could have used area, which would have made really good sense here since I originally started with this graph. The area would have been this area between the trend line and the x-axis. It's just really hard because I don't know what value that is for time. I don't know what time value that is. I would have a really hard time doing area in this case, so it wouldn't be as good here to do it, although normally I would probably favor area since I started with a graph. Since this is constant velocity, I also could have used the equation delta x equals 1/2 v naught of 20 plus v of negative 5 times time of negative 4. So this would be 1/2 20 plus negative 5 times 4. And that would also get me delta x. Now that's only because acceleration is constant. As we'll see, if acceleration is not constant, then I cannot use this equation, and I have to use calculus, meaning I have to use this function that we got from the integral. So from here we could fill out the rest of this. I'm going to pause it, and I'm immediately back with you with all these numbers filled in so you can double check that you got the same numbers as me. Let's try number 3. So we're going to skip over number 2, and let's go to number 3, because I've had a lot of questions on what to do when you have this parabola with numbers and how to get information from that. So let's first do the qualitative graphs by sketching it. So I'm going to look at a window right at the beginning and just say, what's the slope of a tangent line right there? And it looks like it's going to be flat. So that would mean v is equal to 0, and I'm going to plot that v naught of 0 as a y-intercept on my velocity axis. And at the end, if I look at a window right there at time equals 4, it looks like it has a negative slope, which means I'm going to have some kind of a negative value at 4. And I can go ahead and connect that with a straight line representing the negative acceleration that we have with the slope. That negative acceleration should be plotted here. I do want to, while I'm looking at the acceleration, point out that a concave down parabola is going to always indicate here that you have a constant negative acceleration. Concave up would be a positive acceleration. The slope of a velocity time, in this case, the negative slope that we see, would indicate a negative acceleration. And this acceleration time graph has acceleration on the y-axis, and that's why we'd have a negative constant. So each of these graphs depict that negative acceleration that we see in different ways. Concave down parabola is negative, negative slope for VT graph, negative acceleration, and the negative constant here. If we go back to this original graph here, you can see this is also the case where we have a concave down, indicating a negative acceleration, a negative slope, indicating a negative acceleration, and you can see here that our constant here is also negative. Okay. So now that we've sketched the graphs, we're going to start to obtain number values from this. And so first thing I'm going to do is look at this graph that I have given with the numbers and just look at the x and y axis. So the y axis has position x on it, and I can get from x any position x naught, any position x. Delta x is the change, like how from beginning to end. And then I have time on my x-axis. So I can get delta x and t as quantities. And in fact, since I want x naught, x, and t, x naught, x, delta x, and time, I can get all 4 of those things. So for example, I can get my starting position as 10 meters. My ending position looks like is going to be -5 meters. So my delta x is going to be from the beginning down to the ending point, which is going to be -15 meters. And my time is 4 seconds. Next thing I can do, as always, is look at slope. Now, a parabola has an ever-changing slope, but I can look at when it's 0 to indicate that we have a quantity we know being 0 at that time. So that means V naught is equal to 0, and I got that from the instantaneous slope of a tangent line where this is at a vertex, meaning where it's flat. Although I know it's negative, I don't know the steepness of anything after that. So at this point, we would have to calculate something, either V or A or both. And since it's a constant parabola here, meaning it's a constant acceleration, we see that from the straight line graph here where it's linear, and from the constant value plotted here. Since it's constant acceleration, I can use those four acceleration equations that we have. If it was not a parabola, if it was some kind of a weird wavy thing, I would have to be given the function and do calculus. So let's get the acceleration first, and then we can get the velocity using one of the equations, or we can also start looking at how calculus could fit in with this as well. So the acceleration, given the variables we have, the equation that best fits this is going to be this equation that comes from our quadratic shape here, right? It's the parabola that we have here creates the quadratic function we have in our equation sheet. So we have 0 for our V naught, -15. We're solving for A. Our time was 4, and we can go ahead and get our acceleration here. And that's going to be equal to -1.9. Now, I can very easily go to any of those equations that we have that have V in it and solve for the ending speed V. So really any of those equations that we have, so for example, this seems to be probably the easiest one because it's just there's no squares or anything, then I can solve for V by doing -1.9 times 4 plus 0. And that's going to go ahead and get me my ending speed of -7.5. I know that's 7.6 if you do that, but there's some rounding in there. So I'm just going to go with 7.5, although if you do this exactly, you do get 7.6, and that is fine. Okay, so now we're basically done. So I could just write in this function, right? We already have it right here. So v as a function of t, for example, I know should be v equals a times t plus v naught, right? But there's no fun in that. That's just subbing values into our expression. So let's actually start with the xt graph and then use derivatives to get these. So our graph here is going to be described by this function. It's going to be 1/2 at squared, right? I'm using the equation that we have on our equation sheet to model this out as a starting point. So then -1.9 is our acceleration. Half of that is going to be -0.94, and that's times t squared. There is no initial velocity, and we're starting at a position of 10. So if I want to then use calculus to get to this, I would be doing a derivative. That's going to give me the slope function of this x as a function of t. So its slope is velocity, and so if I look at then the derivative, I'm going to bring that 2 out in front. That gives me then 1.9. I'm going to subtract 1 integer power to give me t to the first power, and that's it, which is exactly what we expected if we just subbed in our acceleration for time. If we did a derivative of this one, this is just simply going to be 1.9, and therefore we can use calculus. So the rule that we can follow on this is calculus works for situations where we have constant acceleration, or in situations like you'll see in number 4 here, where it's not constant acceleration. These equations that I was using down here work for constant acceleration because we're assuming a is a constant. They do not work when a is not constant. So in number 4, you're going to notice I'm going to be doing calculus. I am not allowed to use these 4 equations that we've been using because a is not a constant, as we're going to show. Okay, calculus always works, but in general, we use it when we're given functions like this. Algebra works when you're dealing with constants. So if you're given constants, we use algebra. If you're given functions, we use calculus. So let's look at when we're given a function. So notice that this is a parabola, and normally that's when you have an xt graph, right? And the velocity time graphs should be linear, but in this case it's a parabola, which means that we have an acceleration that's changing with time. So I'm just going to first focus in on the calculus stuff. So in going from this velocity time to the acceleration time, we would have to turn this function into a slope function, and we do that by taking its derivative. So the 2 comes out in front, so then the acceleration function would be equal to negative 0.4 times t, because we subtract that 2 into 1, so now we have t to the first power, plus 2, and then that's it. So actually this acceleration is going to have positive 2, and it's going to, I don't know how long it's going to go, oh, 5 seconds, so let's actually plug in and see if it crosses 0. Actually, it reaches 0 right at 5. It's like I planned that and then did these solutions without realizing that. Anyway, so at 5 seconds, if you plug in time equals 5 right here, then you'll notice that the acceleration does reach 0 at that, and I had that planned out so that we're only looking at this part when the accelerations are positive. Okay, so now that we have that derivative done, we can also work backwards to get the position time graph. And so that is going to be graphically what we call area, but in calculus we call area accumulated an integral function, right? So we're going to get the area accumulated function using an integral. So that's going to give us x as a function of t. So that's a little bit trickier. I wrote this out for you so I can talk instead of writing. So we have the negative 0.2 times t, and then we're going to add 1 to this, right, to make it t cubed, and then we divide by that power that we ended up with, 3. Same thing over here. We take that 2t, we're going to add a power, making it t squared, and then divide by that power, which is 2. That gives us 2 over 2 t squared. And then since it's a constant 5, we just add a t to it. And then, of course, we don't know what initial conditions we had for position, like what location we're starting on a tape measure. So I'm just going to assume that that's going to be 0. Actually, we'll just make it 0 because we weren't told that. In a problem, it would have to tell us that it is 0. So if we're going to start here, then we need to know what's happening from there. Now, this is a cubic function, so I'm not going to ask you ever to sketch these cubic functions. So let's just ignore this for now. I can sketch a parabola pretty easily, so I know for example, if I work backwards, the y-intercept is negative 5. I know it's going to have a positive tilt based on that number in front of t being positive, and it's going to be concave down. So this should end up reaching a vertex right here, because then I know that corresponds to a acceleration value of 0. Now, if time equals 5, I have all these expressions here, so I can just start to sub in values. So since we started with the velocity as a function of time, we're going to sub in 5 for time t, and we're going to figure out what value we end up with. I should point out that I had this going to flat to indicate zero, but I didn't need it to have a zero velocity. I don't know what it's going to be. So actually we probably should hold off on sketching this until I know where I'm going to approach. I know it's going to have this shape. I don't know if it's going to look like this or if it's going to look like that, or I don't know what value on the y-axis we're going to end up with. So I probably should not start to just draw it until I know that, because I'm going to actually calculate it right here. All right, so let's start with v naught. That would be when we have time 0, and we already know that that's going to be -5. That's the y-intercept that we have right here. And our v is going to be subbing in time of. So now that I've subbed this in, -0.2 times 5 squared plus 2 times 5 minus 5, you actually do get 0. And so I was justified in making this end at 0, but I didn't know that technically until I calculated that value. When we have a time of 5 seconds, the instantaneous value of A, if we substitute this in, is also going to be 0. So that's coincidental that the velocity is 0 and the acceleration is 0. And then lastly, we can jump over to this cubic expression and just substitute in 5 for t to get our value there. So I went ahead and typed that in while I was paused, and this is going to give me -8.33 meters. And since we're starting from 0, that's also going to be my delta x. Because the position you end up from 0 is the same thing as the ending position if your x down to 0. Now I said don't sketch because you're not expected to sketch this as part of the AP curriculum, these kind of advanced functions like cubics. But you're also allowed to use Desmos on the AP exam. So let's just go ahead and graph this function, and then we could easily sketch it if we were asked to. So I typed in this function. It's -0.2 over 3. Remember that 2 over 2 is just a 1. And so I just plotted this, and you can see for the first 5 seconds, it is in fact going to give us that 8.3, that 8.33 that we saw is about what we have. And so you can see this is the cubic nature. So we don't really notice that cubic right here in those first 5 seconds, but you can see the shape of it. So if we wanted to draw this, we could draw this then and sketch it on there. Right, and then it would start to turn down. It's hard to draw to scale, but all we're really worried about when we sketch is the initial points and then if it's curving any concavity. So I hope that helps, and you can bring in any questions that you have to class or email them. Thanks. See ya.